In this series, I'll walk you through all the steps for designing a race car suspension. In this episode, we'll design together the inboard pickup points. Hello everyone, this is Bruno. In the previous episode, we designed the upright pickup points, and if you missed that, you should go back and watch that video. Now, we're gonna shift focus to the inboard pickup points on the chassis. As a quick recap, we are doing this exercise through a case study where we are designing a GT3 from suspension kinematics. Our goal is to define pickup points for optimal kinematics performance, and we also communicate with the design team to see if there are any conflicts with other parts of the car. Besides that, the focus is on the design process, not really on the specific values for each parameter. And lastly, we are using the design methodology taught in the first episode of the series that you can find in the video description. Quick disclaimer, the values used here are only examples. They are not recommendations for a race car design. Besides that, many important considerations are not taken into account here, since this is just an example. As you can see, we also created documentation for this project, and you'll have access to these notebooks in the video description. In the general documentation, as you saw in the previous episode, we defined what motions we want to use for our simulation, as well as we defined the targets for each of the parameters. Keep in mind that these are just examples, we're not really focused on the values themselves. Now let's focus specifically on the design of the inboard pickup points as can be seen here. So we would have the wishbone pickup points on the chassis, as well as the steering rack pickup point connecting it to the toe link. Some of the parameters that have to be defined before we design our inboard pickup points are, for example, roll center height, lateral distance of the instant center, camber gain heave, anti-percentages, and so on. So let's discuss a few of them more specifically. For that, we also created specific documentation which you can also get access to. So if we look at first the front view parameters, we could be speaking about, for example, the instant center. My goal here is not to describe each parameter very specifically, but just to give you a quick recap. So for the instant center, it can be found in a simplified way by connecting both wishbones and seeing where they intersect. And it will influence, obviously, roll center position, but also the lateral distance of the instant center, determine the camber variation with suspension movement, and also the instant center height changes the wheel track variation as you compress the suspension. After that, we have the roll center. The roll center can be found after you defined your instant center. It will determine the weight transfer, geometric versus elastic, as well as jacking forces and how much the car rolls, or it will at least influence that parameter. Now moving to side view parameters, we have a similar definition for instant center, where we're looking at, again, the inclination or orientation of the wishbones. In this case, looking at the side view, it will determine the anti-features, pitch center, and also the longitudinal position and height will influence caster variation and wheelbase variation. A consequence of the instant center positions will be the pitch center, which influences how much the car pitches under braking, acceleration, or any longitudinal weight transfer. Very connected to the instant center and pitch center, we have the anti-features. These, which could be anti-dive, anti-squat, or anti-lift, depending on which axle you're talking about, will determine or influence the pitch movement of the car, as well as how much geometric weight transfer you have through the wishbones instead of through the springs. Lastly, we can connect the front and the side view. So if we connect the front view instant center, defined here, as well as the side view instant center, we have the instant axis. And we can also create a plane where our wishbone should be placed. As long as the pickup points for each wishbone are within these planes, we're gonna get the instant centers, roll centers, and anti-geometries that we would like to have. However, depending on the specific position where you place your pickup point within this plane, the variation of these parameters could be different. If you want a more detailed explanation on each kinematic parameter, you can check out our seminars. But now, with a brief introduction to them, we can also discuss some kinematics behaviors. And we're gonna start with toe behavior, specifically bump steer. So the bump steer will influence how the toe changes as you compress the car. So you can influence the car behavior under braking, traction, or cornering as well. In this specific example, we'll say that we want to minimize bump steer. It does not need to be the case, but it is our goal for this exercise. In that case, a very good trick is to have your tie rod pointing to the instant center. This is a very good initial approximation for minimizing bump steer, and then you can fine-tune around that point. Next, we want to speak about camber behavior. We know that the static camber is just one piece of the puzzle. When the car is cornering, braking, we have the camber changing for many different reasons. As we can see in this figure, we can see that the outside tire is changing camber. This is coming because the car is rolling, because the tire is deflecting, because the suspension is compressing, and so on. So this is the simplified equation that determines the final dynamic camber. And it will be influenced by the static camber, the camber variation with roll, which is something that we want to play with in this episode, the camber recovery or the camber gain with suspension compression, and with camber variation with steering, which we discussed in our previous episode. On top of that, we also have compliance from the system. Here, since we're working with the instant center positions, we want to focus on the camber recovery or camber gain with suspension compression. Depending on the lateral distance of the instant center, we're gonna get more or less camber variation in heave and roll. But how do we define how much camber gain do we want to get from the suspension system? Well, in the end, what matters is the final dynamic camber. So we will define what final dynamic camber we want to have, for example, when cornering. And based on the static camber value, as well as the roll of the car, compliance, and gain with steering, we have one variable left, which is the camber gain or camber recovery here. For that, we created a simple tool to show you some numbers. This is a tool that can show us the contribution of camber variation from different sources, such as suspension compression, suspension roll, steering, and also compliance. And then if we can look at each of them separately, camber with roll, camber with compression, and so on, or we can look at the final camber, which is the sum of all of them. So here we have some car parameters and steering geometry. And our goal here is to determine the lateral distance of the instant center that we would like to see. Here we are simulating a left-hand corner, meaning that the outside tire will be the right one. We defined that for whatever reason we want to have 3 degrees of negative camber on the outside tire when cornering. Remember also that your tire is deforming, so maybe the real camber is not this one, but it's a good reference for our design. Right now we are achieving 2.6, meaning that we want to have less variation when rolling and when cornering. For that, in order to achieve less variation when cornering, we have to decrease the lateral distance of the instant center. So let's try 2 meters for this distance and still 2.7. And now let's do 1.5 instead. So let's try to be very aggressive with it. And there you go, we achieved the target dynamic camber when cornering for the outside tire. Now that we have the theory out of the way and that we also defined the target for each of the parameters, let's go to our suspension modeling software OptimumKinematics and start designing the suspension. So in our last episode, we finished with a V4 of our suspension and we were happy with the upright pickup point. So let's create a new version, V5, before we start working on the inboard pickup points. So let's start playing with our V5. Let's check the different parameters. I want to start with front view and I want to work with the instant center. We know that the instant center will influence the camber gain depending on the lateral distance, and the inclination of this line will determine also the roll center. So first, let's work with the lateral distance for the instant center. It's the parameter that we have here as front view swing arm length. We have 1.1, while our target, if you remember, is 1.5. So we have to change our pickup points in order to make this point a little farther away from this tire. So a clear option, since the instant center is the intersection of the plane of the 2 wishbones, would be, for example, to raise the 2 pickup points from this wishbone. Just like the previous episode, I'll show you first a manual iteration, how to do that manually, which is not very efficient. And later on, I'm gonna show you how to use an optimizer for that. All right, so to make this point a little farther away, we have to increase the height of these 2 pickup points. Let's change it by 20 millimeters. And we can see that the distance increased and now we have 1.54, which is not bad. Of course, we want to be more accurate than that, but for the exercise, I'm gonna leave it like that. Now we can look at the roll center. The roll center is 88, while what we were targeting for this car was 20. So in order to keep this distance, but at the same time lower the height, it is not enough to change only one of the wishbones. I have to change both of them at the same time. So if I lower both of them at the same time, I can keep this distance the same, the lateral distance, while change its height and therefore lowering the row center. So let's try to do that. And I have to change the height of the bottom wishbone as well. I'm gonna repeat the same 20 millimeters. Let's see what we got. So now the distance is a little shorter than we would like to have, and the row center is lower, but not enough. So we're still targeting 20. Let's keep going and decrease another 30 millimeters. So I'm gonna go through another round of iteration until I get to the parameters that I want. As you can see, it's a very time-consuming process to do it manually. After a few iterations, I got there. We have the lateral distance as 1.5 meters and the row center height as 20 millimeters. Now that we are happy with the front view, let's look at the suspension from the side view. Now we have to work with the instant center of the side view, and we can also display that parameter within OptimumKinematics. Alright, so now we have the instant center of the side view, and we have to look at the anti-dive value that we want to have. Since I don't want to assemble a whole vehicle and run a simulation to understand where we are in terms of anti-dive, I calculated what angle we need to achieve in this case to get to the 40% anti-dive we want. So we are looking for an angle of 4.75 as the side view swing arm angle. Therefore, we need to decrease this angle. Just like on the front view, the orientation of the wishbone planes determines where the instant center is. And to lower this point, I have to play, for example, I can be working on this pickup point over here. I want to lower the inclination of this wishbone. So let's lower the height of this pickup point and see where it gets us in terms of the angle. So now we have an angle, okay, we have exactly 4.75, which is what we were looking for. Of course, these are changing many other things, such as the longitudinal distance and the height. And this will influence parameters such as caster variation when you are braking, or wheelbase variation as the car moves up and down. But we're not too worried about that in this exercise. Once we've fixed the angle, we should go back to the front view and reanalyze the parameters. We can see that the row center was heavily influenced by that change. It went from 20 millimeters to 3, as well as the lateral distance of the instant center. It went from 1.5 to 1.6. So I'm gonna have to run another manual iteration to get back to the original parameters. This will once again influence the side view angle and so on. This is why I emphasize it is so important to use a parametrized model or an optimization for that. So first, in this example, we're using a parametrized CAD model where we have to define as inputs the lateral distance of the front view instant center and the row center height. This will already give us the orientations, at least on the front view of the wishbones. Next, we have to define also the position of the side view instant center, and based on a given distance that we want from the chassis to the wishbones, the parametrized model can tell us exactly where each pickup point should be in order to achieve all of these parameters at the same time. Now, if we're trying to do it manually, it is very time consuming and it requires lots of iterations. So what I want to do here with you, so that we don't spend a lot of time going through these iterations, is to use the optimization. And instead of only looking at these few parameters that we discussed, we can include other parameters such as bump steers that are going to be influenced by the tie link position, as well as Ackermann geometry. I have already created the optimization that will help us find the final V5. First, we define the objectives we want to work with. So what are we trying to achieve with this optimization? We're going to be looking at, for example, camber angle. So what is the camber gain that we would like to have? Instead, in this case, instead of looking at the specific parameter, such as the lateral distance of the instant center, I prefer to work with the final result I'm trying to achieve. So in this case, we're looking directly at the camber gain. We also look at toe angle for the bump steer, since we're trying to minimize and keep it as 0 for all the range of movement for the suspension compression. Next, we define row center height for 20 millimeters. And as I mentioned, instead of defining the anti-dive, we defined a side view instant center angle of 4.75, which gives us the anti-dive we want. All of these parameters were analyzed for a heave movement. If we go for a steering movement, we also want to analyze the steering ratio to make sure that we get to the steering ratio that we would like to have. Let's assume that at this stage we already have an initial C factor from the steering rack to work with. And also the Ackermann angle. If you remember, in the previous episode, we said that in this case, we want to work with a parallel steering geometry. And for that, we are looking for an Ackermann angle, which is the difference between inside and outside tires, of 0, meaning that both tires are steering the same amount. This can be very different for different race cars. We have to also define what is our design space. So what pickup points the optimizer can change, and also what is the box or the area in which they can be changed. So in this case, we can see that we selected all of the inboard pickup points for the wishbones and for the tie rod or steering rack. But also remember that I always say that the inboard will influence outboard and vice versa. It is really hard to only play with the inboard pickup point of the tie rod. It is better if we can change also the outboard pickup point. So it gives us the first example of iteration between outboard and inboard pickup points. Since we're trying to achieve steering ratio, Ackermann, and bump steer at the same time, it is good that we give the optimizer enough freedom to find the best compromise between these three parameters. Now let's run the optimization. Once it starts, for each iteration, it's going to show us the best current pickup points found in order to achieve all of the different design targets we had. Right, so after about 200 generations in the optimization process, let's look at the results we got. So camber variation, it is similar to what we defined. Bump steer is pretty much zeroed, as we can see with the blue curve. Roll center height, which we defined at 20 millimeters, it's pretty much spot on static with some variation. Actually, we can fine-tune this optimization because I would probably like to see a little more variation for the roll center height than we currently have. Side view angle for defining the anti-dive, so we designed it for 4.75, and the best compromise it could find, considering all the different constraints, was about 4.9. We have to then simulate and see how much anti-dive we got. Maybe it's like 42%, which wouldn't be bad compared to the 40% we were expecting. Steering ratio, we targeted 15.0 and we got 15.2, which is not bad. Again, we can fine-tune that further if we would like. And Ackermann angle, we asked for parallel steering, and that's what we got. So for the entire steering range, we only get 0.005 degrees of steering difference between left and right. So that's excellent for a parallel steering geometry. So let's replace the previous V5 with the optimized V5. Right, so now that we have the optimization finished, we should be checking the system. If everything makes sense, and we already saw that the parameters were fine. So we got the camber angle gaining heave that we targeted initially, steering ratio pretty close to what we wanted, side view swing arm length angle for the anti-dive close to the number, and also the roll center very close to 20, which was our target. Toe angle gaining heave is basically the bump steer, which is basically zeroed, which is what we wanted. We also have to put it in the final assembly of the car to make sense that it does not have any conflicts with other systems. In case it does, remember that we can fine-tune the design space for each pickup point to always make sure that they are in a place that is feasible in the context of the design. Alright, so let's say that we are happy with V5 and we are ready to document this version and also submit it for revision, so submit to the design team. As I mentioned in the previous video, it is very important that we keep track of all of the versions that we worked on and we properly documented. So first, I'm keeping a copy of all of the pickup points in case other people have to access it easily. And then I'm gonna say which pickup points I changed in this version. So all inboard pickup points, as well as outboard toe link. So for the parameters changed, in this iteration, we were focusing on roll center height, instant center position, anti-dive, bump steer, steering ratio, and Ackermann. And for the comments, I'll just say that we used the optimization module for this iteration. Right, so let's submit this version to the design team so that they can review and see if we have any conflicts with the other system. And this was the feedback we received. After adding the proposed pickup points to the vehicle assembly, we request the following adjustments. Number 1, the lower forward pickup point that would be this one here. So lower forward needs to go 10 millimeters forward in order to be close to a chassis node, which we know it's very important for avoiding compliance, and also for avoiding interference with other components. All right, so we're gonna have to move this one at least 10 millimeters forward. And number two, the inner pickup points. So all of the wishbone inner pickup points should have the same Y coordinate for ease of chassis manufacturing. So in this case, we want these two pickup points, or they need these two pickup points to have the same Y coordinate, as well as these two pickup points. So if we look from a top view perspective, we can see that the Y pickup points are slightly different. This means that, let's say that it's a tubular chassis, for example, then it's a lot harder to manufacture this chassis. So making it simpler will also simplify the chassis design and manufacturing. This is a positive feedback because changing the Y and X coordinates of wishbones is not that hard. Why? If you remember earlier in our discussion, once we have defined the planes containing the wishbones that initially were defined using the instance centers, but now that we have the initial pickup points, we also have the plane of the wishbone. As long as we keep the pickup points in that plane, the behavior will not change a lot. This means that once we change the X coordinate, we just need to find a new Z coordinate that would keep that point within the plane. The same is valid for changing a Y coordinate. So this is what we're going to do. We adjust X and Y as required. We calculate the new Z coordinate to make sure that it is still contained in the same plane. And then we run simulations. We can compare the previous design with the new version, adjusted version, and confirm that the behavior didn't change much. So let's make these adjustments. We could use CAD file, for example, or a simpler geometry tool in order to define the planes and find the new pickup points. For the tool that I'll use, I have already defined the pickup points that we found, and I have to define the plane for each wishbone. So if I select the 3 pickup points, we know that 3 points define a plane. Now I have to find the new pickup points within this plane. In the case that we have to change the Y coordinate of both wishbones to be the same, upper and bottom, it can be a good idea that we use a line and we define a new pickup point in this line. This ensures that the angle of the wishbone is not tighter than before. So it is something that we might want to do. Besides that, we also notice that these wishbones are pretty short, so we can use this opportunity to make them a little longer and possibly make the chassis a little narrower. So we can do that for all of the pickup points in order to adjust the Y coordinates and the X coordinates as required. And with that, we are going to find our new V6 after we implement the changes from the feedback. Right, so now that we have V6, which adjusted Y and X coordinates, we were able to run simulations, and we are going to confirm that we do not see big changes compared to V5, even after the adjustments. So since we are changing the position of the wishbones, it is very important that we check camber angle variation, which is what we're checking here. And actually, after I plot both versions, the change is really minor. So as I told you, as long as the change is not large and that you also keep it within the plane, we should see a small variation. So that's very positive from the perspective of camber angle. Next, we're going to look at row center. So the row center, we see a very minor change, particularly for the variation, which is what I've been telling you. The variation can change a little bit, but I would say that this variation is still acceptable. Next, we're going to look at anti-dive percentage. Initially, we targeted 40% and we had a small change. So it went from 39.75 to 39.25. It's a 0.5% variation for the pitch center. And I'm going to accept that this variation is small enough for me to disregard it. And lastly, we always double check the bump steer because it can change dramatically with a small change. But in this case, even though it seems like from the plot that it changed a little bit, when you look at the y-axis, it's still pretty much 0. And with this, we confirm that even though we adjusted the wishbone pickup points without using any optimization, only by adjusting using a parametrized model, we were able to keep the parameters the same and make the rest of the design team happy. Good, so now we are ready to document the last version that we created for the inner pickup points, at least for this iteration. So we adjusted wishbone inner pickup points as per request. We tried to keep all parameters the same, and we did succeed. And as comments, I'm gonna say that we used a parametrized model to keep all pickup points in the same plane. Alright, so now we can submit V6 back to the design team so that they can double check that all of our changes were exactly like they expected. So I just showed you all the steps that I follow when I am designing inboard pickup points. So I hope that with that, you are able to design better race car suspensions. Please remember that you can have access to all of these notebooks and documentation shown here in the series in the video description. If you like this content, you might be interested in our seminars. We have a vehicle dynamics seminar which covers all the different perspectives of vehicle dynamics and kinematics in a lot more details than what we've done here together. And we also have the performance engineering seminar where we teach dozens of different techniques in data analysis and performance engineering to use and exploit 100% of the performance of a car. Besides that, these are the services that OptimumG offers. Vehicle dynamics consulting, where we could, for example, help you to design the suspension of your race or passenger car, among many other vehicle dynamics services. We also offer performance engineering, where you could have one of our engineers at the track with you. And finally, we offer simulation software in the areas of kinematics with OptimumKinematics, vehicle dynamics, and tire modeling. Thank you for watching the video. If you have any questions, leave them in the comment section so that I can get back to you, and I'll see you in the next one.